Fractions can appear in word problems, as we have seen before. And let's revisit a family of word problems and solve a problem now. This one, though, will involve a variable in a denominator. Now here, remember that we talked about work problems, combined work problems, or sometimes called work rate kinds of problems. Suppose we are filling a bathtub, and if we're using the cold valve only, we open up the cold water valve and the tub will fill in 8 minutes. Then we drain it, and then we experiment with both valves open. We open both the cold and the hot, and it fills in only 5 minutes. Now, with that information, we ought to be able to figure out how long it'll take if only the hot water valve is open. And we're going to say that that amount of time is X number of minutes. Now, you may recall that we had two ways of setting up problems like this. One way was to build our equation according to what is going on in 1 unit of time. The unit of time here is minutes. And we have to first identify the fraction of the job that is performed by our cold water valve. You see, the cold water valve takes 8 minutes. What fraction of the job can be done in 1 minute? You see, what fraction of the tub can be filled? If it takes 8 minutes to fill the whole tub, then in 1 minute, 1/8 of the tub is filled. That's the idea. With the two valves working together, it takes 5 minutes. How much of the tub is filled in 1 minute? Well, 1/5 of the tub is filled in 1 minute. Now, what about for X minutes, for the hot water? See, it doesn't matter how many minutes here. The fraction of the tub that is filled in 1 minute is this fraction. You see, if this number is 6, then 1/6 of the tub is filled in that 1 minute time frame. All right, these are key elements when we start to build the equation according to what's going on in 1 minute. You see, in 1 minute, here's the way we're building the equation conceptually. The amount of the tub filled by the cold water valve plus the amount of the tub filled by the hot water valve is the amount filled when they work together. You see, it's each one separately, add those together, and we get the amount when they work together. So that's the idea. The amount filled by the cold water valve in 1 minute is 1/8. That's the part of the tub that's filled. By the hot water valve, it's 1 over X from up here, and working together, it was 1/5. And now we have an equation involving fractions. The common denominator among 8 and 5 would be 40, and we have an extra factor of X. So we have 40X as the common denominator. So 40X times this term, 40X times this term, 40X times that term. And now we can see the cancellations, 8 into 8, 1, 8 into 45. This is 5X times 1. The X's go out here, leaving 40, and on the right, 5 into 5, 1, 5 into 40, 8. 8X times 1 is 8X. Now we solve as we normally would. I'm going to come out here to the left and just repeat what we have here. It's a fairly trivial situation, and all of the tough part of the problem is done. So if I subtract 5X on both sides, I get this. So 40 is equal to 3X, and dividing on both sides by 3, I find X to be 40 over 3. But what's that? Well, 40 over 3 is, if I divide 3 into 40, I get 13 and 1/3. And what was this? Well, X was some number of minutes. You see, it was X number of minutes for the hot water tap to be used. So it's 13 1/3 minutes that would be required if the hot water valve was used by itself. One of the most important things we do in mathematics is build equations for solving word problems. Now, sometimes those equations are kind of delivered to us as a formula because the problem itself, by its nature, lends itself well to that formula. Other times we have to build our equations ourselves. Now, sometimes those equations that we build come from kind of a discussion within the problem, and we've looked at situations like that. Work rate problems, for example, they fall into a family. We structure the equation a certain way. Now, right now we're going to talk about a kind of problem, or a family of problems, referred to as variation problems. And the first kind of variation we're going to talk about is direct variation. And these kinds of problems emerge when words and word phrases like varies directly and directly proportional are used. For example, if it says y varies directly as x, or if it says y is directly proportional to x, those mean exactly the same thing, and they imply the existence of a constant k such that y equals k times x. Now, this idea of direct proportionality is really not so foreign to us. We haven't seen it in this kind of format maybe before. But, you know, we could say something like, gee, the circumference of a circle is directly proportional to its diameter. You see, I mean, doesn't it make sense that, right, here's the circumference, the distance around the outer edge of a circle. Here's its diameter. And as the diameter gets bigger and bigger and bigger, the circle gets bigger and bigger and bigger. Or we could say at the same time that as the circle gets bigger and bigger and bigger, the diameter gets bigger and bigger and bigger. Gee, what does that have to do with this idea of relationship? Well, if the circumference is directly proportional to diameter, it implies the existence of a constant k such that the circumference is equal to k times the diameter. Now, through experimentation, we find out for all circles in the world, that constant of proportionality happens to be pi. You see, so we don't have to do any experiments here. We already know that constant of proportionality is pi. Now, for some relationships, though, involving variables, and for some things, things like automobile mechanics and other kinds of areas of industry, we have these variations that we can establish, and through experimentation we can find the value for k involved with that particular idea, with that particular item. We'll see an example or two in just a second. All right, let's come back here though and talk about this constant k just for a moment. I want to make sure we understand about direct proportionality. Suppose k is found to be 3, and suppose I make a table of values here. And I'll let x take on values 0, 1, 2, 3. And y then, if x is 0, we have y is 0. If x is 1, 3 times 1 is 3. If x is 2, 6. If x is 3, 9. You see, so as x is increasing, y is increasing, but more important than that, y is increasing at a certain rate, a rate which is proportional to the change in x. X is changing by 1 each time, y is changing by 3 each time. That's the idea. K could be negative. If k were negative here, then these values would be negative. And so as x is getting bigger, y is getting smaller. That's not the important thing in direct proportionality. The important thing is the rate at which these are changing. These are changing by 1, these are changing by 3. So what if it's in the negative direction, you see? All right. Now, in the kinds of problems that emerge with direct proportionality, a lot of times there is a statement about this direct variation occurring in the problem. All right, that allows us to establish a very general kind of relationship between variables. For example, here it says y varies directly as x. All right, that allows us to say, or to write down, that there exists a constant k such that y equals kx. And often in problems like this, there'll be some information, sort of like information that comes from an experiment. And that information might be like this: when x is 5, y is 3. Now, when that occurs, as soon as we have information about x and y in this direct variation format, we can put that information into this relationship and find the value of k. So when x is 5, y is 3, so y is 3, x is 5. You see, this allows us to solve for k. We divide on both sides by 5 to find k to be 3/5. But if k is 3/5, we put that back into the relationship, and now we have some real grit, some real good information about the relationship that exists between x and y that allows us to answer questions about one or the other. For example, What is y when x is 20? What is y when x is 20? Well, with this relationship, we can certainly figure that out. When x is 20, we get a cancellation here. 3 times 4, y is 12. So y is 12 when x is 20. Here's another more practical kind of example. According to Hooke's law, the distance a spring is stretched is proportional to the force on the spring. The distance a spring is stretched is proportional to the force on the spring. This is all that it's saying. Here's a spring. It's just relaxed right here. There's no force on the end of it. If we put some force on it, it'll stretch. And the distance that it stretches is proportional to the amount of force. If we put more force on it, it stretches further. If we put less force on it, it doesn't stretch as far. That's all that it says. Now that seems to be kind of an obvious consequence of having a spring and putting force on it, doesn't it? But it's an important idea that allows us to establish this relationship. Now, distance is related to force, a direct kind of variation. So, let's see. We could say then, if the distance is directly proportional to force, it implies the existence of a constant k such that the distance is k times f, k times the force. Now, if we have any information about a particular spring and how far the spring stretches, we can actually calculate the value of k. And that's what it says in this problem. It says something about that. It says a force of 50 pounds stretches a spring 5 inches. Now it's important to know that a force of 50 pounds will not stretch every spring 5 inches. You see, we have this proportionality, but it involves one spring. It's not like with circles, because with this proportionality that's established worldwide. This is for one spring, and that's what's kind of important in these kinds of problems. All right, so 50 pounds stretches 5 inches. Let's come over here and understand what's going on. That here's the spring at rest. We put 50 pounds on it. It comes down to this level. The stretch is 5 inches. See, that's all it says. Now, mathematically, that tells us that a distance of 5 inches is associated with a force of 50 pounds. And this allows us to find k. Divide on both sides by 50. And we find k to be 5 over 50, or k is 1/10. Now, if k is 1/10, we can jump right back into our relationship and write that relationship as distance is 1/10 times f, times force. And that allows us to answer such questions as these. How far will a force of 20 pounds stretch the spring? A force of 20 pounds. Let's come back over here and figure it out. How far will a force of 20 pounds stretch the spring? Well, replace the force with 20 and solve for d. That distance then would be 1 times 2, 2. So that would be 2 inches. All right, next question. It says, what force is required to stretch the spring 1.5 inches? What force do we need to be on the end of that spring for it to stretch exactly 1.5 inches? Well, with this relationship, we can figure that out. A distance of 1.5 inches is associated with what force? That's what this is saying. Multiply on both sides by 10, and we find F to be 15, and that's 15 pounds. So 15 pounds of force is required to stretch the spring a distance of 1.5 inches. Now, springs can be different, and that's why we have this idea of establishing with some experiment a value for K. Inclined planes also have this varying quality about them from one inclined plane to another. Here's an example. The distance a ball rolls down an inclined plane is directly proportional to the square of the time it rolls. During the first second, the ball rolls 6 feet. Now let's understand that last sentence. We have an inclined plane, and during the first second, the ball would roll 6 feet.
Well, let's see. The problem is proposing that we find a mathematical model that relates the distance traveled to the time. Now, since we're told that the distance varies directly with the square of time, that implies the existence of a constant k such that d is equal to k times t squared. Using the information from our experiment about the distance of 6 feet corresponding to a time of 1 second, we simply replace into this relationship and solve for k. Of course, 1 squared is 1, and we understand now that k is 6. Now we can rewrite our relationship, replacing k with 6 into the equation. So here's the mathematical model that was requested. Let's understand what we've done. Now, we were given a basic relationship between distance and the square of time, and that gave us the existence of k. And then, using information from an experiment that a distance of 6 feet corresponds to a time of 1 second, and replacing within the relationship, we built this mathematical model. Now, the model can be used to give us a distance that corresponds with any given time that we'd care to consider, or a time that corresponds with any distance that we care to consider. But let's realize that this distance and time relationship is true only for this particular inclined plane. That is, if we considered a different inclined plane, then the original experiment would be somewhat different. In 1 second on this inclined plane, for example, the ball might roll 10 feet. So our value of k would be different for this particular inclined plane. Well, let's go back to our original inclined plane and continue with our problem. The next part of the problem says to find how far the ball will roll during the first 2 seconds. Well, in order to discover this, of course, we use the relationship that we just developed. And in this equation, we replace t with 2. Of course, 6 times 4 is 24. We're talking 24 feet here. So we know that the ball will roll 24 feet in 2 seconds.
We've talked about mathematical models in which one variable changes in direct proportion to another. Well, there is a mathematical model for inverse proportionality as well. Here's an example. If the problem says y varies inversely as x or y is inversely proportional to x, these mean the same thing. They both imply the existence of a constant k such that y is equal to k over x. Now notice that the other variable is in the denominator over here. The constant of proportionality is still in the numerator. And with direct proportionality, that constant k was also in an implied numerator. And that's kind of an important idea here. Now we can get an idea for how these variables change with one another a little bit by letting k take on a specific value. If k takes on the value like, let's say 3, then we might set up a table of values for x and y and make a few observations. Let's let x take on values 1, 3, 6, and 9. Now, if x is 1, we have 3 over 1, 3. If x is 3, we have 3 over 3, 1. If x is 6, we have 3 over 6, 1/2. If x is 9, we have 3 over 9, 1/3. What I want you to notice is that as x is getting larger here, y is approaching 0. Y is approaching 0. And that's the nature of inverse proportionality. As x gets bigger, positively or negatively, y is going to approach 0. Now, under direct proportionality, as x, as one variable, moves away from 0, that is, gets bigger positively or negatively, the other variable will also move away from 0, either positively or negatively. And there's a little switcheroo in there when the constant is negative and all of that kind of thing, but that's the idea, that both variables are moving away from 0 under direct proportionality. Under inverse proportionality, as one variable moves away from 0, the other one is moving toward 0. That's the fundamental difference. Okay, let's build some models here, and we're just going to be very general about this building process. This one says a variable, varies inversely as the 4th power of t. So we would write this, a equals a constant of proportionality over, because of inverse, you see varies inversely, means that the other variable involved here is in a denominator. So and it's the fourth power of t. It's not just t, it's the fourth power of t. So we write t to the fourth in the denominator, and that's all there is to it. In this one, we have what's called joint variation. A varies jointly as L and W. And this is like a double direct variation. We would write A equals a constant of variation times L and times W. You see? So all of them are in an implied numerator here. We can have variation involving several variables. One maybe directly and the other inversely. Here's an example. It says z is directly proportional to x and inversely proportional to the square of y. So just with that information now we would have z is. Now put the constant of proportionality in the numerator, and then all of those variables that vary directly with z go upstairs, and all of those that vary inversely with z go downstairs. And that's all there is to it. So we have, let's see, z is directly proportional to x, it goes up here. And inversely proportional to the square of y, y squared goes down here. And that's it. Now, this problem goes on and allows us to manipulate our relationship a little bit further. It says z is 15 when x is 5 and y is 3. Now, this information about our three variables allows us to identify the constant of proportionality. Let's do that here. Z is 15 when x is 5 and y is 3. All right, so we go through and solve a bit by, let's see, this is 9, and we'll multiply by 9 on both sides. So we have 9 times 15 is equal to 5k, and 9 times 15, gee, that's 135. So I'm going to come up over here. That's 135 then is 5k. And dividing on both sides by 5, we find k to be 27. Now, if k is 27, that allows us to take this information and put it right back in here, and then rewrite this relationship as z equals 27x over y squared. And we could go from here and answer various questions that may be posed in the problem.